Hello guys, welcome to my YouTube channel. Today we are here to solve Leetcode problem of the day, and today is 23rd Feb 2025, and today's problem is construct binary tree from pre-order and post-order traversal. So from the title of the problem, it seems like you have to find out binary tree and you will have pre-order and post-order traversal of the tree. But if you can remember that only from the pre-order and post-order traversal you cannot you cannot create the unique binary tree. There might be possible that there will be multiple binary tree which have which will have same pre-order and post-order traversal. So so to make a unique binary tree you must have in order traversal with either of them pre-order or post-order traversal. So this is the title of the problem, and let's begin with what is the constant are given here. The pre-order dot, the length will be, maximum length will be 30, and both are, and pre-order dot length. Okay, all the values of pre-order are unique. Less than, and pre-order each pre-order dot length, what does it mean? Okay, all the value of the pre-order are unique, and post-order length and pre-order length both should have, will have the same length. And you can see, and what, all the value of the post-order as well are unique, and it is guaranteed that post-order and pre-order are ordered traversal and post-order traversal. It means that both pre-order and post-order traversal of the same binary tree. So this is the problem. Let's begin with the problem statement now. Given two integer array, pre-order and post-order, where post-order is the post-order traversal of the binary tree of distinct values, and post-order is the post-order traversal of the same tree reconstructed and returned. So what you will have to do, you will have to reconstruct the binary tree and you have to return the root of the binary tree. And here, as I have already mentioned before, that only with pre-order and post-order traversal you cannot predict the unique binary tree. You cannot construct a unique binary tree, but there might be possible that there is multiple answers, so you will have to return any of them. So let's see the example one. 1 2 3 4 5 6 7 8. So this is the pre-order and the post-order. So the output is, you can make it from this output, you can make it, I will explain it later. And then there is one more example, pre-order and post-order is 1 and the output is 1. So how we will approach this problem, let's see. I will also explain that how only pre-order and post-order cannot be able to predict the unique binary tree. So you are given here 1 2 3. Let's begin with another example. Let's say that it is 1, and let's say it is 2, and then it is 3, let's say it is 4, and then let's say it's 5. So in the pre-order, how we compute the pre-order traversal? Pre-order, so it will be have like root and then left and then right. This will we will have to first print the root and then left subchild and then right child's subtree. I mean, so in this binary way, if you will try to find out what is the pre-order traversal, then at the beginning we will print the 1, again the left child, okay, left, then we will print the 2 and then there is no left child and we have already printed the 2, so the right child is 3. So we have computed, we have already printed the left subtree and the root, and now we will traverse the right subtree. So there is no, because we reach it 4, so there is no left child, so we will print the 5. So this will be the pre-order traversal of this graph. So now let's see the post order traversal. We will first explore the left child, then right child, and then root of the tree. So that will the from here we will goes to the left and there is no left, so here is the one right, so we will print the tree, and now 2 we print the root. So we will goes to here. Now we will have to explore the right subtree first. So here again we reach it here, there is no left child, so here is the right child, so we will print out. So now we have 4, again now it is 1. So what we can see here, that always at the beginning in the pre-order traversal and at the end there will be the root of the binary tree. But if from the one if you try to make the, if you will do the reverse engineering and if you will try to reconstruct the same binary tree, you cannot be able to reconstruct. Maybe you can reconstruct multiple in multiple of the binary tree. There might be one of the binary tree that will be equal to this binary tree in the structured way. So let's start to try to reconstruct it from it. So let's say 1 is there, so there will be a pointer here, then we will move the pointer to here. 2, from the 2 here it is 2. So what we can say, that okay, 2 is there, so 1 is the parents and 2. So because 1 is here, so these all the node, we cannot say that these all node will be in the left subtree, but we can say that these node may or may not be the left sub be the part of left subtree. So let's assume that this is the left subtree part, so we will do the 2. Okay, we will add to the left subtree of this node. Now we move to the next node, so again the 3. So the here it is the 3 and it is showing that it is left of the left of this node. So it, you cannot say, let's suppose that here it is the root. If you will consider it as the root, you cannot predict that which node, the node that is explode before this current node is either the left child or right child, because we explore something like this: left, right, and then root. So if you consider this as root, so this has been root, so these might be the possibility that either because we only have the one node, so it might be the left child or right child. So we cannot say that either it was the left child in the original tree or it was the right child of this node. So this is the position where we cannot reconstruct the original binary tree from the pre-order and post-order traversal, and these are the limitations. So these are the limitations. So if so we can construct multiple, there might be the multiple binary tree that can be reconstructed from the given pre-order and post-order traversal. So let's try to. So our problem says that we do not have to worry about if either we can be able to reconstruct the original binary tree, but what we have to do, we just have to construct a binary tree that should have the given pre-order and post-order traversal. So I erase the post-order traversal. Let me write it now. It will be 3. Oh shit, where is that? It will be 3 and then 2 and then 5, 4 and then 1. Okay, all right. So this is the post-order traversal. So what we can do, how we will approach the problem and how we will come with the solution. So we will again make a pointer, start a pointer from here as well as the pointer, because you can see in the problem statement that the constant are very low, like 30. The array will have only the length of 30, so there is very flexibility in the constraint. So what we can do is we can first see it is 1, so we will append 1 here as a node, and we will also store a map. Why do we need a map? Because, and one more constraint are given here, that all the all the pre-order values are unique and all the post order values are unique and all the pre-order values are unique. So you do not have to worry about that there might be the multiple nodes with the same value. So here it is 1. We can we can make a node and with value 1. There might be some address 8, something like, maybe say that's address. So this will be the one node, and again when we see the 1, so we will move this pointer to 2 and we will see that who might be the parents just right to the current node. So we will see where it is 2, so we will find it that it index 0, 1, 2, 3, 4. At index 1, here it is a 2, so we will check that who will be its parents. So from here 5 have not been visited, have not been included in the tree, 4 also have been not included in the tree, so 1 have been included. So whenever we will get it 1, we will find the node. So let's say it's the parents, so we can say parents equal get, we will get the value of 1. So we will get the address of 1 and we will check either it has the left child or not. If there is no left child, we will add a left child with the given value. So we will add a left child 2 and we will store it 2. We will store it 2 with the address like 2, and maybe its address is 200, whatever the address. We will again append the 2 as a child of this node. So again we will move the pointer to the next index. So it is 3, so we will check the 3 Okay, it is the tree. And now first we find what is the index of this. Here it is the tree. From 3 we will check which node have been added to the tree. So we will see which is the leftmost node that has been added in the tree. So we will check that here it is 2. Okay, so from the 2 again we will, here it is the 2, so we will find out that what is the address of this 2 node 2. So it is the 200. So from, we will check either is left child are present or not. So we will see that, we can see here that left child is not present, so we will add 3 here. Okay, and again we will store the map 3, and there might be the address of 300 of this tree node. So again from 3 we will move this pointer to the next, so we will get the 4 here. So first of all we will find out where it is the, where 4 is available in the post order traversal. So we will find it index 3. So from the 4 we will check that who will be the root of this node. So which leftmost node have been added in this tree. So we will find out 1. So from 1 we will get the address, and we will check either left child have been added or not. We will see, we can see here that there is already a left child exist in the constructed binary tree. So we will append to the right of this. So we will append 4 here. Okay, then we will move the pointer to here 5. So we will check where the 5 is available on the post order traversal. So we will move till here that 5 is available at index 2. From 2 we will find out which is the leftmost node that is already been added in the vanity. So from here we will reach it here. We will check either 4 is available in the map or not. So let me, in the previous iteration we didn't add 4, so this 4, and let's say this is 400. So we will move from index 2 to 3, and we will see that 4 is already been added to the index. So from 4 we will find out the address of this node. From we will check that either 4 have any left child or not. So we will check that, okay, it has no any left child, so we will append 5 here. So we will move the next pointer, and we have reached to the end of the array, and our binary tree have been constructed. So this will be our approach, because you can see that we have constructed the binary tree, and this is not exactly similar to the what we have constructed at the beginning to find out the pre-order and post-order traversal. This is the pre-order and post-order traversal of this tree, and similar pre-order and post-order traversal we can get from these what we have reconstructed here. So this will be our approach. So if we can say in the few words, we can say that we will make a pointer to the pre-order traversal, and at each index we will check where it is present in the post order traversal. After the post order traversal, we will, after finding the after finding the value in the post order traversal, because all the values are unique, so whenever we will hit on index where the current value are present in the post order traversal, we will find out what is the next leftmost node that is already been added to the tree. We will mark it as a parents, and from parent we will check it, and we will pick up that values, and from values from the map we will find out what is the address of that node, and from that node we will check either if the left child is present or not. If there is no left child, we will add the current value to as a node to the left of this parents node, and if already been there is some node that is already been added to the parents, so what we will do, we will add to the right of the parents node, and we will also add that current node to the map so that we can use it further. So this will be our approach. Let's now code it now. So it is very easy problem, if we can say how. Now, as I have discussed, that we have need a map, that is integer versus string node. Oh, okay, and map the output and pre, because in the pre-order traversal, the very first node is always the root node, so we can consider it as node. Okay, now new tree node from pre-order. Okay, we have to return it this, so we will return that matter. Okay, this will be our solution. Now we will move it each index in the pre-order traversal. Suppose it is n, and equal to pre-order of, sorry, so from here suppose a new index j, because we already have been added 1 0 index, so we will not consider it. So we will start it from 1 index because we have already added the element that is present at index 0 in the pre-order, and we mark as root of the given binary tree. Okay, while j is less than n, and as I have told you that we have to just find out, first we will find which is the index of the current current value at index I. Post order of j is not equal to, suppose child, if I say child equal to order of is not equal to, until we will not find out the index of the current value, we will increment j. Okay, whenever we hit from here, we will have to find out the leftmost child that has already been added, that has been already been added in the tree. So from here, post order of j. Okay, from post order, but we will have to check it here. We'll have to check it here. We will have to find out, we have to check map dot contains key, that is not contains key. Till we will not find out, we will just increment the j. Whenever we will find out, what we can do, then we tree node we will mark it as parents equal to map dot get post order of J. Now we will have to check if parents dot left equal to null. We will add that node parent dot left equal to node and we will add the child. Okay, and then we will add in the map dot put parent dot left dot value equal to, oh here we have, okay, so it's correct now. So if there is already a left child, what we will do, we'll add it as right child. So dot right, add it, and then height of this one. Okay, I think it's done now. So you can see it here. We have started from index 1 and we will check it out that which node. We will first find out where it is the index, where it is present in the post order traversal, and then check where who can be the potential parents. So from here we find out the parents, from parents we will get it, and from the parent dot left is null, we will add as a left child. We will put it in the map, and if it is not, we will add in the right child and we will add that node in the map. Let's try to see it here. So it's saying pre-order, you have not. So he cannot post order. What is, so all will be in the small case. So that's an order. Oh sorry, post order, and there is anything left? No, it cannot get map. Sorry. So you can see that these two test cases that is available as an example in the description have been passed. So let's try to submit it now. So you can see that our code have been submitted and it's 53.87% of the people who have submitted in Java, as well as the memory. You can see we have consumed 43.55 MB and beats 41.6%, 67% of the people who have been submitted in Java. So this is all about the problem. And one more thing left, that what will be the time complexity of our code. So we can see that here, if the length of the pre-order and post-order traversal is n, so you can see that from here we are n because we are iterating the pre-order traversal, and corresponding to each pre-order we are trying to find out the index. So this is the n, and it will be the, this combined will be n. So the time complexity will be n square. Let's try to see it here. What No, it's wrong. It's wrong. The time complexity is n square. Why? Because we are iterating each index here, and corresponding to each index, first we are trying to find out where is the this value present in the post order traversal, and corresponding to that we are to find out who will be the potential parents. So regarding on the basis of that, we are marking it as the child of the leftmost node that is have been added in the so this showing the wrong time complexity is not order of n in our code in this code we the time complexity is n square. So I don't know, they might be have some issue in the algorithm that they have written to find out the time complexity. So this is all about, and one more thing, that what will be the memory constraint. In the memory constraint we are trying to store each node, so the time complex space complexity is order of n, because corresponding to each value we are storing it their node. So the time complexity is order of n, and the sorry or the space complexity is order of n, and the time complexity is order of n square. So this is all about the problem. If you have any query or suggestion, you can ping me below in the comment box. Stay healthy and keep growing. If you find my videos helpful for you in coding, you can like, subscribe. Thank you.